Just had a good break? Probably not, right? Working in the lab?
I feel better. I feel more caught up, but I just need to polish.
I posted the new homework.
Okay. My integrals are messy and
Okay.
it took me forever to get the constant right.
So these integrals, mostly you can find in like in
I know,
like Mathematica, MATLAB.
I know, but I was
You don't have to. When I was in college, we had to do all the integrals by hand, right?
I like it.
Now you don't have to do that. So I want to quickly finish this chapter and start with the band structure. In 15 minutes I can finish this. Yes, everybody. Okay, let's get started. So last time we talked about the Hall effect, right? So far we have been talking about this very important for who are doing experimental research. So we were measuring something called the DC conductivity, right? So that means we are passing current or voltage that is basically not changing with time. Right? Then if you measure the current also basically constant. So, but this is completely different when you apply your voltage or current as a AC current. So in that case your conductivity, this sigma, that is this frequency dependent, right? That conductivity can be microwave frequency, it can be maybe megahertz radio frequency. So if you have any sigma, so this we call the AC conductivity. So this has two parts. It has a real part of sigma plus imaginary part of sigma. Typically we say sigma 1 plus I times sigma 2. Real and imaginary. If you have a DC part, you don't have this one, right? So you only have the real part. So that is typically given by that NE squared tau O M. So today I want to talk about a little bit how if you do the AC conductivity. That means basically you are applying your, say, electric field that has both your frequency dependent part and also time dependent part, right? So it oscillates with this frequency omega. So now, if you have electron, if you apply this AC field, so then you can write your that relaxation time approximation. What is that? Your net force, F net, is basically given by your change of rate of your momentum, right? So this is given by what? This is given by E times E, right? Force is given by E times, but E is basically, suppose this doesn't matter, this one, that is your force. What is the next term? Anybody remember? In the relaxation time approximation, next term is P over tau, right? So that P you can write, I write P over tau. This is also, so that momentum also then will have, so this momentum also will have omega and T dependence. In the DC case, there's no omega dependence, so T dependence, right? It's a constant value. So if you do this one, then I can write my P also has this kind of behavior, P omega times E minus omega T, right? That's the momentum. So now if you plug in into this equation, what is dP over dt? That you have, say, P omega dP over dt. So this doesn't have T dependence, right? Only T dependence coming from this one, that you get minus I omega. Then you have E minus I omega. Is that right? Equals E times E omega. Then you have E minus omega T. Then you have minus P also I can write as P omega times E omega divided by tau, right? So now you can see I omega T all cancel. What you have is, if you take your P omega, what you have here is, on this side you have 1 over tau, right? Minus I omega equals E omega. Now you can see, you can write your P omega as E omega, because this E has now omega. So this can be some, say, microwave electric field. So then what is the frequency? Typically microwaves, they have gigahertz, right? If you apply RF radio frequency, that's typically megahertz kind of frequency. So divide by I omega tau minus I omega. Okay, so that's it. So now you calculated your P as a function of omega. If it is a 0, DC, what will happen? Your omega is 0, right? So then you get, you can see E tau. So you get the same value. So now if you know P, then I can write J, the current density. Anybody remember how do you write the current density? E times N times velocity, right? Everybody should remember that. So then velocity I can write as P over M. So that means if you write this one, you get En divided by M. P I can write from here, that is E times E omega. So then J also should be frequency dependence, right? Omega divided by, I just plug in P here, 1 over tau minus I omega. Very simple. So what is this? It's nothing but N E squared over M times, I can take tau upstairs, right? Take here, then I get here 1 minus I omega tau. Fine, right? So tau, then we get I omega tau times E omega. This is J omega, Now what is this? This basically Ohm's law, right? J equals sigma times E. Remember, J is always sigma times E. If you take J and E, this must be your sigma. So now if you write that, you get sigma omega equals simply NE squared tau over M times 1 minus I omega. You remember this one, right? If DC case, omega is 0, remember NE squared tau over M, that was due to conductivity, right? Now you have this it has a real and imaginary part. So if you do this one, just, you know how to write this one. You just multiply by the conjugate of this one. So then what happens to the denominator? 1 plus omega squared tau squared, right? If I multiply by 1 plus I omega t, then I get NE squared tau over M times 1 plus I omega tau. So do this, you get simply NE squared tau over 1 plus omega squared tau squared plus I N squared tau over M. Okay, also we have M. I just write. Yeah, like this. N squared tau over M times 1 over 1 plus omega squared tau squared plus I times omega tau over 1 plus omega squared tau squared. That's it. Because sigma omega is given as this. This is the AC conductivity. You can see you have both real and imaginary part. So you can see if it is a zero frequency, omega is 0, this whole part is 0, right? So then you get this a simple DC conductivity. But if it is a AC excitation, you get the real and imaginary. So what is your real part of this sigma? Is NE squared tau over M times 1 plus omega squared tau squared, right? Imagine part of sigma given by omega tau divided by M times 1 plus omega squared tau squared. This is very important. So if you are working on AC conductivities, you have real and imaginary. If you use a DC, this part is 0, right? Omega 0. Then you only have to worry about this part. You can see this part also becomes 0. If you plot this one, actually, they look like this. If you plot omega tau as this sigma, your real part will look, if you plot, say, log part here, something like this. Because when omega tau goes to a very large number, so this becomes 0, right? So if you look at this is the real part. If you look at the imaginary part, actually 0 for low frequencies, but here you are going to see some kind of, and this part, this is the imaginary part. This is very important when you work on like microwave conductivities and things like that. So you can follow this one. I have all the derivations here, everything I talked there. You can see this is the real part. So that this part is we call the sigma 0, right? So this part is called the sigma 0. 1 plus omega squared tau squared. Imagine part 8 is, I have not written that one. Okay. So that is basically the real and imaginary conductivity. Now we need to connect these conductivities to something called a dielectric constant. This is another thing I think a lot of people make mistakes. So let me clearly write down that one. So dielectric materials, so dielectric can be large band gap semiconductors or insulators, right? Typically dielectric, it can be dielectric constant can have omega and that K dependence of both of them. So typically we write this D as, if I have a material, if I have external electric field, then my polarization is always opposite direction, right? So we always write this one as epsilon 0 E plus your polarization, right? So then also we write D in terms of epsilon E as, everybody should remember this one, epsilon 0 times epsilon R times E. Epsilon R is called relative dielectric constant. For AR this is 1, right? So epsilon 0 is some constant value. So this is exactly true for magnetism also. If you have magnetic material, if I have external field H, your inside, instead of polarization, we have something called magnetization. That can be this way or this way, depending on diamagnetism or paramagnetism, right? So in that case, we write the effective field B, that is more like D, as mu 0 times H plus or minus M, right? So then also B you can write as mu 0 mu R times H. So mu R is called relative permeability. These are exactly same idea. So you should be able to connect each. Okay, so in this case, now I can write, if you take this one, so epsilon 0 is constant, E is constant. If you take these two, then you have, just take this way, epsilon R minus 1, right, equals P, right? So that means I can write epsilon R minus 1 equals P over epsilon 0 E. Right, so now just remember when we were talking about the plasmons. So if we have some metal with some lot of electrons, right? So they respond to the electric field and make something called the plasmons, right? So they have this plasmon frequency given by some in this over M epsilon 0 something, we showed that one. So now let's see how that was for metals. Even the dielectrics also have some free electrons, right? So then how do they respond to this one? Again, just like we did in our, if you remember, we had some length L, then by polarization we had some positive charges here at the distance x, and we have negative charges here at x. So then we calculated something called the polarization, right? If you remember, that polarization was what? Polarization means total number of dipole moments per unit volume, right? What is the dipole moment? Basically charge is given by this distance x times a times e, that is the charge, right? Charge times n, that's the charge times length L is that's the dipole moment, divided by volume. Volume is A times L. If you remember that one, A and L cancel, this is basically E n times x. So please remember, your polarization is given by, I can write this one as E n x divided by 0. Okay, so now let's see how we connect this E and X. So this is because we are responding to some external electric field, right? So then if I write my Newton's second law, if I have a particle electric E with mass m, how do you write the Newton's second law? Mass times, if you do in the one dimension, this equals E times E, right? So now since we are talking about this AC electric field, right? We are talking about not DC. So that means I can write my E as some say E0 times E I omega t. So then your X also becomes this oscillations, right? That also becomes some X0 times E I omega t. So now if you use this one, what do you get here? Just substitute here. Mass times, what is d squared x over dt squared? I get I omega twice, right? You get squared, then you get x0 e I omega t equals e times e also I can write as e0 e I omega t. You can see e I omega t cancel. Then what I get is I squared minus 1. So then minus e doesn't matter the signs. You get basically omega squared. Actually, you don't have to do this one. You can directly write this one omega squared m omega squared, then x0 e I omega t is simply x, right? Equals e0 e omega t is simply e. So that means I can write x as e divided by m omega squared. Now just plug in here, you get En over epsilon 0 E. X I can write as E divided by m omega squared. Okay, that's it. So if you do this one, what do you get? You get epsilon r minus 1 equals Ne squared divided by epsilon 0 m times this 1 over omega squared. So if you remember this one, anybody remember this one from the plasmon? This was the plasmon frequency, omega p. So omega p squared is given by Ne squared over epsilon 0 m. That means I can write epsilon r as 1 plus this one. This one I can write as omega p squared. Yeah, actually we have a negative term coming here. This should be 1 minus. Yeah, 1 minus, because we had negative term. That I squared had negative 1, right? Yeah. Omega p squared. Oh, that's it. So you can write this real part of your dielectric constant as 1 minus omega p squared over omega squared. This is very important relationship. What does this mean? Your real part of your dielectric constant, if I plot omega as epsilon r, when omega p is omega, your epsilon r becomes 0, right? So suppose this is my omega p. So at this point your omega r becomes 0. For omega is larger than omega p, then this is positive. When omega p is smaller than omega, so then this becomes negative. You have this kind of relationship. This is omega p is 1. So you can see here. So this is what I wanted to explain. So So is the derivation is clear for everybody? Please go through this one. So you get, so epsilon r, or epsilon, yeah, in this case, yeah, the frequency dependence epsilon is given by 1 minus this omega p squared over omega squared. So this is how it, omega, the epsilon, real part of epsilon with respect to omega. You can see the relationship, right? When omega is omega p, that epsilon r becomes 0. So this is exactly what happens. So that means if you have this frequency, suppose it is say few hertz, so that means your frequency is very small, right? So that means they don't really pass through your material. Suppose this is my material, I have some wave coming that has a frequency that is small, so smaller than your omega p. So that means that the amplitude of that wave will basically die down inside the material. So that means they just decay here. But if your frequency is much larger, what happens? They can go through the sample, right? So that means they pass through the sample. That means your sample become transparent in this value, so they become opaque because they don't pass through, right? So that's why plasma frequency is very important. So how they respond to the light. So here you have light passing through, right? So that's the transparent. So this is basically attenuation. So we know for each metal you can calculate your plasma frequency, right? Because that is given by this n square tau over m. Omega p is given as omega p squared is n squared over m. If you have lot of free electrons, your plasma frequency is much higher, right? So that's why metals have much higher plasma frequencies. Okay, so now let's quickly go with the thermal conductivity of metals. Everybody remember the thermal conductivity part? So what was the thermal conductivity? Everybody should remember this equation, right? Thermal conductivity is usually given by 1/3 of your heat capacity times V squared tau. Very important. So if you have a metal, typically what kind of velocities are important? Only the electrons with velocity closer to the Fermi energy, right? So everything else doesn't matter, because if it is like this, only the ones closer to the Fermi surface, or in this case, if all filled, only the electron at the Fermi energy, they are important. This doesn't matter, they are always filled there, right? So that means, but CV, we have, don't get confused, this CV we are talking about now electronic component, right? So first we talk about CV coming from phonons, right? The 3R value and T cube value. What about the electronic part? Anybody remember? For electronic part, how does CV change with temperature? It's linear. Remember we did that long integral, so we showed your CV is given by some pi squared over 3 some n e squared and all. Then we had some t here. So let me remind you, and I cannot remember that exact expression. So if you write this one, yeah. So this is the value, if you remember. Pi squared over 3 times k squared NEF times T. So what is NEF? That's density of state at Fermi energy. But in the homework, you showed what is that NEF. I asked you to show it is depend on the EF and N, right? So you can easily show NEF as 3NO. I think everybody did that one, right? 3NO. Now if you plug in this one, you can easily show. So just calculate for 1 mole. That means N is for 1 mole. So then you get 3 N over per unit volume. So then if you plug in that one, so that capital N becomes simple N, right? So this is per unit volume. So the same function T, except this N becomes just the number of electrons per unit volume, right? N is N per. Is that clear? So then you can see why this was 3. Why did we get 2 here? You had 3 over 2 here, right? So that 3 and 3 cancel, you get 2 here. Be careful that, right? When you write K, you had 1 over 3, right? When you plug in this one, you get pi squared over 2, this one. That is this CV value. This is a very important thing. Remember, phonons, we had high temperature, we had 3R. Low temperature, we had TQ, right? Value. But electronics part, they always have T dependence, linearly T dependence. Please remember that one. Phonons depends low or high, but electronic part mostly T dependent. It's very important. I think you will see this one in this equation. Okay, so now we can use this one to calculate this K. Let's plug in these numbers here. So you can plug in everything. So K, the prime thing per unit volume, you have 1/3. Then you have the C value is what? Pi squared over 2. Then you have KBT. So I write KB squared N times T, right? Over EF, that coming from that density of state value. Then we have to calculate only the velocities near Fermi surface. So we'll replace all the V's by VF. Is that clear for everybody? So basically plugging these numbers. Now this EF you can write as half M VF squared, right? E is basically now you can see VF squared cancel, this one cancel, then you get basically pi squared KB squared N over 3M times tau times T. This is your K price value. You can see this one. So I'm getting some really interesting result here. Yeah, if you do this one, that here, pi squared KB squared N tau divided by 3M times T. So that is this one, right? Now is the fun part coming here. So this fine, right? K prime. So now if you remember your sigma was N squared tau over M, right? The Ruder conductivity, DC conductivity. Now if you take this ratio, K prime over sigma, what do you get? You can see here, pi squared KB squared N tau over 3M. And if you divide, then I have M over N squared tau times T here. Now you can see this one, M and M cancel, N and N cancel, tau cancel. So you get really simple expression. See, this thermal conductivity to electrical conductivity part is given by pi squared, the Boltzmann constant squared, divided by 3E squared times T. Or if I take T here, what's that? Very simple formula, right? If you do this one, actually, yeah. So this pi squared, k squared divided by 3 squared. Can you see it? Really interesting relationship here, this thermal conductivity to electrical conductivity ratio at a given temperature doesn't depend on anything, not the mass, not the n, not anything, right? It's only depend on this very fundamental constant. So actually people have seen this one in the past. At a given temperature, if you measure for any metal, if you take the ratio, that's always a constant. So this means what? This is electronic part, right? K is from electronic. The sigma is also electrical. Your electrical conductivity and thermal conductivity ratio for a given temperature is always constant. But if you change T, that changes. But for a given temperature, that ratio is constant. That means if I try to increase my electrical conductivity, thermal conductivity also increases, right? If I try to decrease my electrical conductivity, thermal conductivity also decrease. So that's really interesting thing. So this is the biggest problem for people working in this thermoelectricity. So thermoelectricity, I said there's something called the figure of merit. That is given by this Seebeck coefficients, let's say Q squared sigma over kappa. That's the definition of figure of merit. You can make Q large. So that's good, right? So to make C large, what do you have to do? You have to increase sigma and decrease kappa, right? So but we know this sigma is constant. So there's nothing you can do there. So because if you try to increase this one, you can never decrease this one. But people found way to do that. So what can you do? Actually this kappa is really two components, right? If you take for the sigma, this kappa means sigma divided by, you have the phonon part plus electronic part. So if you divide everything by say sigma, this is the part we are talking about here, electronic part. That is, you cannot do anything, but you can work on this part, right? So you can increase the, actually decrease the phononic thermal conductivity. So then you can make this C large. So how do you increase the phononic thermal conductivity? You have to introduce more phonon scatterers, right? So if the phonons can scatter without affecting the sigma. So there's a lot of work going on this one. So you can see how this one, but this is actually called the Wiedemann-Franz law. Wiedemann-Franz law says electronic thermal conductivity and the electronic conductivity ratio is always constant. So actually these people had noticed long time ago. So this like 1853 people had seen all the metals have almost same that ratio if you measure at room temperature, because T is constant, right? So then with this theory, now we can show K over sigma T is a constant, right? So this number is called the Lorentz number. So because that's a constant, right? That's given by pi squared kb squared over 3 squared. So that has a value given by, you can calculate that value is about 2.45 10 to the power minus 8 J over ck squared. Okay, so this is remarkable, right? It's independent of n, m, tau, anything. Here are some of these ratios. You can see 0 degrees. All these metals, they have almost the same number, right? Slightly different. If you even 100, see, these two are different, right? Because, but at given temperature, they are pretty constant. That Lorentz number. Okay, so then we talk about the last thing, thermopower. So far we talked about electrical conductivity, we talked about Hall voltage or Hall coefficient. So next thing I want to talk about is the thermoelectric power. Sometimes we call this one Seebeck coefficient. So I don't know whether you are familiar. There are two very important effects. One is called the Peltier effect. Peltier effect. Other one is called the Seebeck effect. So Seebeck effect means if you have a material, suppose this one, if I can maintain some temperature difference between the two ends, suppose this is slightly warmer than this end, then you will always see some voltage across that one. That means by introducing delta T, you can get a delta V. Right? So what is that basically? That's a power generation, right? Actually that day, remember, we had that demonstration, we just heat from two ends, so then you can even run a motor. That's basically Seebeck effect. You give some temperature gradient, that will give you enough power. Peltier is the opposite of that. If I can apply or maintain some voltage difference across a material, I give the power, then with respect to one end, I can cool the other end, right? So now, given delta V, I can create a delta T. I apply some voltage. The same thing we showed you in that one. If I can connect it to a power supply, I can make one end very cold. I can even make it as cold as ice temperature with like 5 volts. So that means you are giving voltage and making delta T. What is that basically? It's a refrigerator, right? So there are, actually already there are commercial refrigerators based on this thermoelectric. So this material is very important. We call the thermoelectric material. So typically these voltages are very small. We are talking about microvolts per Kelvin. But now we have, because of new materials, we can make this one even millivolts. So that means if you put several in tandem, you can make volts. So if you can cool both ends, now we can make several volts even to run a motor. So that means it all depends on this something called the thermoelectric power or Seebeck coefficient. This is the same thing, sometimes we call it the thermoelectric power or same as Seebeck coefficient. Basically we say it's Q. So the basic definition is this. If I have like here, if I have this end at little higher temperature and T, you have a temperature gradient, right? Gradient increases this way, that means your temperature gradient is in this direction, right? This way temperature is increasing, that's where the so then you have an electric field. That's the thermoelectric field. So if you do this one, actually what happens is if you have temperature difference, your charge carriers are going to move from hot end to cold end. So in this case, if it's a metal, so electrons are moving this way. So then if it is like a whole conductor, it always positive charges are moving from hot end to cold end. So that means you have a charge imbalance, right? You have more charges in one end compared to the other end. That means you have a electric field, right? So typically we can say if it's a metal, you have electric field in the opposite direction of your temperature gradient. So delta T is in this direction, then the electric field is in this direction. We define the thermoelectric power as this electric field. This is not the one, this is very important. This is not external electric field. Please remember, not external field. External field means if you apply a voltage source, you have external field, right? This is without any external source, it generates because of the charge accumulation from the temperature difference, right? So there's nothing. So this is all internal. This is no external. It's all internal field. So then we define this thermoelectric power as E equals thermoelectric power times your grad T. That's the definition of your thermoelectric power. Q is called the thermoelectric power, TEP. Is that clear? So, or you can write, suppose this distance is delta x. So then you can write your E, you can write as delta V over delta x, right? Because of this field, you have potential gradient, right? So you have the one end you have V, other end you have V plus delta V. Whenever you have electric field, you have potential difference. So that means E I can write as, so E is Q times grad T. So E you can write as delta V over delta x. Is that correct? Electric field is potential gradient equals Q times what is grad T means? Temperature gradient means delta T over delta x, right? This is. So that means delta V is Q times delta x. Or we write Q as delta V over delta x. So this means if I maintain temperature difference delta T between these two, if I have a potential difference delta V here, so the Q is defined as how much voltage per unit, sorry, delta T is, because this delta x cancel, right? Delta V is Q times delta T, Q is delta V over delta T. So what is the unit? Volts per Kelvin. Typically these are volts is, you can never get volts, right? Typically we are getting microvolts per Kelvin. But there are new materials, they get much higher. If you have a metal, Q is always a negative number. If it's a semiconductor, we'll talk about that one later, holes and electrons. So they have, so that means actually Q, sine of Q will give you the sign of your charge carrier. Your charge carrier. That's just like Hall effect, right? If you have a electronic Hall effect, it's negative number. If it's coming from, later we'll talk about the holes, it's positive, right? So same as if you measure the thermoelectric power, if it's a positive number, we can immediately tell your majority carry is holes. If it's a negative number, it's an electron. So this is a very straightforward way to, because remember, if you want to measure the whole voltage, you have to apply a magnetic field, right? But this is much easier. You only have to make one end colder than the other end, just measure the voltage. It's very simple. What we do is, in our setup, we have a simple heat attached to one end of the sample. we just simply give a heat pulse. So then this ends and becomes hotter than this one. Then we have some two thermocouples attached here. Then we measure the voltage. This one, when this one is on, we will see your temperature is the voltage increasing. When it turns off, it's coming back. From there you can easily measure the Q. Very simple technique. We, like every day we do these measurements. Okay, so now we can calculate your thermal power in very basic way. So like I said, when I maintain this delta V, we have this temperature difference, right? That's because you have charges moving from one end to other end, right? So actually we can take that voltage or the velocity of these carriers actually move in one direction. Some carriers move in one direction, suppose other carriers move in other direction depending on the charge, right? Positive or negative. I can write my this VQ value, that means the velocity of these electrons due to this field here, right? So under this field, if you have a positive charges, they will move this way. If you have negative charge, they will move this way, right? So that means this is VQ is basically average of moving left and to right, right? So I can write that one as half of that VQ moving, I say it is V, moving to right. So that you can write the wave equation, you can write as, this is x direction, x, if it is moving to right, that is x minus v tau, right? Everybody remember? If your wave equation, if you have x minus vt, if it is a negative sign, means it is moving to right, because if xvt is 0, x equals v times plus vt, right? That means when t increases, x increases. If this is x plus vt, what happens? If this is 0, x equals minus vt. That means when t is increasing, x is going opposite direction, right? Please remember that one. So anything you going to, this is going to right, you can write as this way, minus the ones going to left is, how do you write? X plus vt, right? That's it. So if you do this one, I can write this one. Now we can expand this one as a Taylor series. If you remember this, you can write as Vx times, then I have plus, then this one you have minus Vt times dV by dx, right? And if you next term, V tau squared 1/2 d squared V over dV squared. You know how to write the Taylor series. We'll just write only the first term. Then minus, next term I can write as same Vx plus V tau, right? Sorry. V tau times dV by dx. Next term is what? So half V tau squared d squared V over dx squared. I don't want to write this one. Everybody remember the Taylor series? F x plus V t, something I can write as fx plus Vt times df over dx plus half Vt squared d squared over dx squared, and so on, right? So we'll not neglect the second term, we'll write only the first term. If you do this one, you can see this Vx cancel. So here minus V tau they add, then you get 2 V tau, right? So if you do this one, It's very simple. You can see if you write this one, you have half, then you have negative 2v tau times dv over dx. You can see this 2 and 2 cancel. You get v tau negative v tau times dv over dx. Exactly. So now this v times dv over dx I can write as a differential of v squared, then you have to divide by 2. Right? If you differentiate this one, what do you get? 2v times dv over dx, the 2 and 2 cancel. You can write this way, right? You can see what I am getting at. Later, I can do this one like half mv squared, right? That's the kinetic energy. Is that clear how we write that one? Please follow this one. That's very simple. Now, also now this v squared I only considered x direction, right? But you have y and c. So that means if you want to take the real three-dimensional velocity, that is actually 1/3 of this one, right? Because we know this each one is v squared, then one should be 1/3 of the total one. So that means if you divide by 3, then you get v squared over 6. Exactly. Because this is only vx. If you take the three-dimensional v, you get 1/3 of that one, right? Times dv squared over, yeah. So this one, v squared, vq, yeah, this 1/3 and 2, that is 1/6 if you write this way. dv squared over dx squared. What is that really? d over dx v squared I can write as d over dt times v squared times dt over dx, right? So first you do this one. What is this dt over dx? Actually that is temperature gradient, right? That is grad T. That's what here. dv squared over dt times grad T. This is simple, right? So you can just follow that one. So that is my Q due to the temperature gradient. So now, if I at the end, so these electrons will move and finally they have to come to a steady state, right? That's when you introduce your thermoelectric field, right? So that field will make the more charges, prevent more charges being accumulated, just like in the Hall effect, right? Remember, they are trying to accumulate here, so eventually it will create Hall field to stop further accumulation of charges, just like that. So this, it will introduce this electric field to stop further accumulation of charge. Otherwise, all the charges will indefinitely accumulate at the end, right? So that means it has come to end by introducing this VE. So then if you do this one, you can write your this is the velocity, right? So your velocity due to this charge separation should be equilibrated with the velocity coming from the this thermoelectric field. So if you introduce that one, so how do you get this velocity? Electron, whenever you have electron flow, you have electron velocity, right? That is given by, if you remember from the free electron theory, we showed your V is given by E tau over m. If you remember this one, relaxation time approximation, that is basically nothing but your total force is given by P over tau, right? So P is basically mv over tau. From here you get your V is given by E tau over. We did this one, right? Remember this one? This is the electric field from outside. So this is the relaxation time from the lattice part, because lattice introduced this force, right? So by collision, from there you get V. So then we get this VE coming from this one. So then this VE should be equal to the VE coming from VQ here, that is tau over 6 dV squared over dt times grad T. So now, yeah. So now if you play a little bit, then you can calculate your E. This E you can write in terms of all these values. Your tau also here, right? You can see this tau and this tau cancel. So your electric field is basically what you get here. M over E, 6 is here, right? Then you have d over dt. I put m also inside here, v squared. So if I take 3 here, then I can put half here, right? Half mv squared. Yeah, E equals m. Yeah, that's it, right? So what is this one? Half m squared, the energy. Energy over derivative of energy is what? That's CV, right? You C is given by du by dt. So that means this is basically C. You can see here, C. This part here, this one you can write as C divided by 3E. So if you have n number of, yeah, I think n should be somewhere there. So you can find this one. So Q is given by, sorry, from E. Oh yeah. So E is this one. So if you E is given by Q times delta T is here. So this is the definition, right? If E is here, delta T is here, this is nothing but the Q. So that's why you Q as 1 over 3E. So this is energy per the integral, you get CV. So because CV is typically given per unit volume, right? So that's why you have this one. That's it. So now you can write your Q as, yeah, this is the final answer. You can follow all these derivations, it's nothing complicated. Your Q is given as, this is the final answer, CV divided by 3E times N. This is CV is here, the heat capacity per unit volume. Okay, so now let's take the classical case. If you take the classical case, what is your CV? Simply 3 over 2 kBT, right? Sorry, yes, kB, because we take energy is 3/3 kBT. If you take the derivative this one, if you plug in here, then your Q becomes, C becomes now 3 over 2 times En. Then you have so you have CV 3 over 2 kB, then divided by 3En. You can see 3 cancel, you get C, basically kB over 2En or something. 2E. Maybe N you have to do here somewhere. kB over 2E, some constant value. Yeah, oh yeah, because this is per unit volume. You have N cancel. This is the classical value for Q. So that means any material you have same Q. Right? That doesn't make sense, right? But if you remember in the quantum case, what was CV value?
3R.
CV was that you had that pi squared over 3, then it is kb squared, all these, and n, something like this. Only depends on your directly with t, right? That's the classical case. So in that case, now you can again plug in here. So then what you get? Q is 1 over 3 En times Cv, you can buy this one times t. So that means Q has some constant times your linear dependence of t. So it's over here, you can see. So this is that's the basic definition of Q, right? E equals Q times grad t. Q we showed this one. In the classical case, if you use this one, you get Q as this one. But in that free electron case, we found this one to be some constant times t, right? Please remember the Cv is always linearly t dependent. If you plug in here, so Cv, I will put that number. This is very important result. For metals, you can explain your thermoelectric power by this equation. Also, it will be linear dependence. If you have any metal, your thermoelectric power will look like this. It's very linear. Thermoelectric power temperature is very linear. But it's actually a negative number, right? It's more like this, linearly going to 0. It's a linear value. It's negative number. But later we'll talk about, for semiconductors, it's completely different. So metals, your thermoelectric power goes like T. For semiconductors, that's what we are going to discuss later. Semiconductors, Q goes something like some constant 1 over T. That means it's actually going like this. But at the end, it should come to 0. Right? Even here, your thermoelectric power, if it is a negative one, it's going like this 1 over T. Eventually, it will come to 0. But metals, they always have linear T dependence. These are important things to remember. Okay, I think that's the last thing. Yeah, so please read any details here. So only thing, so far we talked about free electron gas. So we showed some certain things can be successfully explained by this theory, but there are a lot of shortcomings. So that's why we need to introduce we call it nearly free electron model of periodic potential model. So in this model, everybody remember what was the basic assumption? So we had this potentials coming from each one. So ideally they were more like this, right? But we completely assume that to be 0, right? That was pretty crude approximation. So next class, so we can get started. We will introduce real potential to the system. That means your lattice is really interacting with your electrons. So here we pretty much neglect the presence of lattice, except they collide with the lattice, right? So because it doesn't accelerate infinitely, so they always collide. That's the only presence of your ions. So, but now next chapter we will introduce the. So we'll start there and finish the class. You get the idea, right? So just write down here. I already uploaded this lecture. So now we are going to actually. So this is what we found. We discussed this one. So previously, remember, my potential was, we take this one as 0, right? Now we introduce some periodic potential. So this is also not the perfect potential, but it's much better than considering 0, right? So can somebody write this? Now we have to solve the Schrodinger equation, right? Previously it was so easy because we had u0, right? So if you take z squared psi plus u r whatever psi equals e psi. So previously u was 0, so easy, right? It's the second order differential equation. Now we have some finite potential. What is the potential? You can write this one. U in one dimension, this ux is, you have some constant value plus some cosine, right? In this case it's a cosine term. I can write this one as some constant, that's a negative number. u0 is a negative number, right? This is less than 0 because that is below here, right? Time plus some constant u1. u1 also, u1 is actually, say, because this one has to be more significant, right? So u1 has to be larger. Times what do you write? How do you write this function? Cosine is a periodicity. So each point separated by a, right? That's the lattice parameter is a. So this one you can write as what? 2 pi over a times x, right? You have the periodicity of a. So that is the potential we are going to use. Still it is pretty. If you do this one in the Schrodinger equation, this is going to be very complicated, right? So, but we have some tricks to do that. You understand what we are getting at, right? Okay, so now if I write my potential like this, ux as u0 plus u1 cosine 2 pi x over a. This a is important, that is periodicity. Because u0, u1 both are negative, we'll assume u1 to be large, otherwise we don't have any effect, right? So now if you do this one, let's consider one situation. If u1 is 0, then it was just like before, right? If u1 is 0, that means same. So that means you get the same. So that means your energy should be simply at k squared over 2m. Then your solution should be some AEI kx minus omega t. In this way, I kx, like that, right? That's same as before, right? If u1 is 0, so then you can write parabolic, yeah, kx minus omega t over omega t. Yeah. So now, if u1 is not 0, then it's different, right? But if you consider the situation, say k is very much smaller than pi over a. So what does this mean? K means 2 pi over lambda, right? Is very much smaller than, actually not this way, much smaller than, this is pi over a. That means lambda is very much larger than 2a, right? Lambda is very much. So that means if you have this one, so this is a, so lambda is much bigger. So that means it doesn't have much effect, right? Because almost like having no periodicity or any modulation. So because lambda is much bigger than a, so that means your solutions are still similar to the free electron modulus. So the wavelengths are much larger than, so wave function and energy bands are nearly same as before. But if they are less than pi over a. So in this case, you will start seeing effect, right? Because now your wavelengths can be something like this. So that now you have to be careful. If this is the case, what will happen? Actually, the sum of the waves can get scattered, right? Remember the brilliant zones, all these waves can get reflected. So that means you can have some waves moving this way and some waves moving this way. That means you can write the solution for this one as what? You can write one moving one direction, say A, E, I, Kx minus omega t. Then if you have opposite direction, going minus B, I, Kx minus omega t. Like this, right? Moving back and forth. So that means you can have, this can be plus or minus. So you can have waves moving, so back and forth. That's why I have minus k outside. Yeah, this one should be minus k. So this means you have one wave moving one direction, one move in other direction, but they can combine in two different ways. So one is you can add the two, next one is you can subtract the two. You have the superposition can happen two ways, right? So in this case A and B are different. So that is when k is equal or less than pi over a. Just imagine k is exactly pi over a. This is very special. What is that? Remember, if you take the first brilliant zone, we know this is pi over a. This is your first brilliant zone, right? That means your k is exactly your pi over a, because you have this wave function k x minus omega t, but this k is same as the brilliant zone boundary. So that means this is very strong, the backscattering exactly happening at this point. So when this happens, your A and B should be equal. So in this case, A and B can be different, right? Because they are not exactly happening at this k value. It can be maybe this something close, but not too far. So, but now it is happening exactly at these two ends. So that means your this A and B should be equal. So that's the case we are going to consider. So if a k is exactly pi over a, they are strongly backscattered. That is, if you remember, that is nothing but the backscattering, right? So then you can write your wave function as this A and B are equal. I can write as, say, C. Then I can have two waves, because you can have, if you have two waves, they can superimpose. We call the superposition. They can be, then you make something called standing waves, right? So you can have two different standing waves, because standing waves, one coming from this positive sign, other one coming from the negative sign. So that means you can have standing waves, say, like this one, and also you can have at a different position, like still standing waves at two different positions, depending on your plus or minus. So that's what we are going to discuss in the next class. So this opens up a lot of new physics, band gaps and everything. You get the idea, right, what you are trying to do? Basically, we are going to start at k equals pi over a, that means the backscattering waves. Then you have two waves with the same amplitudes, C. So you have one wave with positive one, the next wave with negative one. Then you have one psi plus and one psi minus. Let's start from there. Okay, I'll stop here. Okay. So please look at your homework. So I put a new homework for next week. So that one, the first problem is very simple. It's only take maybe 10-15 minutes. So second problem, you have to be careful. I gave graphene band structure. Typically we write EK as K squared over 2m, right? So that's basically when you calculate the density of state, we need this dE over dK, right? You can, for that problem, you can do exactly same way, except this is not EK. That is given as EK as some that has some K value instead of this one. Now it's easy, right? Only you have to do is the dE over dK, that's all. Everyone remember how we did the density of state? Basically, dN is dE, dE. So then, instead of doing this one, we calculate from dK. We calculate dK by doing that. So only then, when you want to calculate dE, basically dK divided by dE over dK. Everything is same. Only this one you have to, don't use this one, use that new dispersion relation. Very simple, it's also very two lines. Don't make this mistake. For graphene, this is not valid. Graphene is a special, like we call the Dirac fermions. They don't have the parabolic wave function. If you have any question, come and see me. Yeah. Everybody remember doing dk, right? Dk is actually, you have to do two-dimensional. Okay? Dk is basically dk times dk is basically, if you take two-dimensional case, basically you take 2 pi k dk divided by 2 pi over L squared, right? That's how we get dk, very easy, right? So you can see there's a k here. So that is dk. L squared is basically the area. That's it. So you can easily do that one. Don't use this one, that's only. Answer, maybe you can go. He must be here.